Hey everyone, in today's video we're going to talk about Newton's law of gravitation. We've mentioned it in the past, talking about when we were talking about forces, but we're going to look a little more in depth um, today and see how to apply it in different scenarios. A lot of this should seem like a review, I hope, different parts of it, but hopefully you'll take something away. The one thing, so this first example we'll talk about is just the forces on two, if we have two bodies, how they're going to interact with each other given some distance. And then we'll look at an example where we have two masses in space, and if we want to add a third one, where would we put it so we know that if we put another object in the center of this coordinate system, that it won't have an acceleration. So looking at this, we should assume that there's probably some mass somewhere down here countering the two forces from gravity or the acceleration at some point at the origin. And then we'll look at an example where if we have some planet and we're trying to shoot something off this, I guess project something off this planet and not a rocket. We're not going to talk about just something with some initial velocity is trying to escape from this planet, how fast that initial velocity would be. And we'll be able to think of that backwards and think of something that comes from a long distance to this planet, and we'll be able to figure out the velocity. So that will just be really which way, where we put our bounds of integration if we're going from the planet out or vice versa. Depends where we start. And then we'll revisit our two masses orbiting around each other. We're not going to really work through a full problem. I'm just going to kind of point out all the ideas. I think we've talked about everything it covers, but we'll look at it once again and kind of just make sure that all these ideas that we're putting together are clear. Okay, so if we look at the first example and we see we're given a mass of planet 1 or whatever this object is, mass 1, and then we have mass 2, and they're separated by some distance r. These aren't rotating or anything. They're static in our initial situation, and what we want to do is find out the force that's being applied on each of these. Well, we know that from Newton's laws that each of these are going to have an equal and opposite force on one another. So if we find one, we know the opposite or the other force on the other object is just going to be equal in magnitude in opposite direction. And so a while back when we were talking about forces, I gave us this equation to calculate the force of gravity, which is known as Newton's law of gravitation, where we have this big G, it's just a constant multiplied by mass 1, mass 2, divided by the radius squared, how far they're separated from one another. And big G is just equal to 6.67 times 10 to the negative 11 Newton meter squared over kilogram squared, which should be pretty obvious because we're getting a force here, and we have meter or kilogram squared in the numerator, and we have meters squared in the denominator. So when we look at these units, our kilograms will cancel with these 2 kilograms, our meters will cancel with these 2 meters, and we're just going to be left with newtons, which is good because that's what we're looking for. So this problem is pretty straightforward how it's written. We know what mass 1, mass 2 is, and we know their separation, and then of course G is a constant that we're also given. So really we could just plug this in, all of our values in, and we should be able to come up with the force that each of these are applying, which when I plug this in, I got a force of 7.16 newtons. So we know that mass 1 is being pulled on with a force of 7.16 newtons, and mass 2 is also being pulled on with 7.16 newtons. And so these values this value seems pretty small, how hard these are pulling on each other, but keep in mind the gravitational constant is 6.67 times 10 to the negative 11. And then we are squaring the radius that they're separated. So unless we have huge masses, the force from gravity generally isn't very large. Now looking at our second problem and applying what we learned from the first, we should be able to solve and figure out if we have two masses, they're drawn on this Cartesian coordinate system, and we are going to add a third mass of 25 kilograms somewhere on this coordinate system. And what we're looking for is that if we put a object in the center, some test object, we want to have zero acceleration, so no force, which of course means no acceleration. So our goal is to find out where we would have to put mass 3 in our on our coordinate system, and given that its mass is 25 kilograms. And then over here we're told what the mass of mass 1 is, mass 2, the x location for mass 1, x location for mass 2, and then our y value for mass 1 and mass 2 are the same in the situation. So we know that we're going to be using Newton's law of gravitation equation, this F of G equals big G m1 m2 over r2, but the problem is what we're looking at is a point at the origin, and we don't actually have a mass there. So instead of talking about force in this problem, we could just think of, well, if we get rid of the mass at some point that we're interested in, we're just considering the acceleration that would occur from some mass, we could get rid of that and just represent each of these as an acceleration. So we know if we had some point we put here, there's some acceleration if we multiplied whatever mass we put, we would end up with this force of gravity. But we're just going to consider the acceleration from each of these. And since acceleration is a vector quantity, we could sum these together using the superposition principle. A1 plus A2 is just could be treated as one vector. And so what we're doing is we're trying to find a third vector that is opposite to the sum of A1 and A2. Just like we did, this is basically a force table, only we're going to just consider accelerations. So what we can say is we're interested with an acceleration equals to 0 in the x direction because we don't want it to move there, and we could say that the sum of accelerations in the y direction equals 0. And so to get each of these, we know that our acceleration A pointing towards mass A, so this is the magnitude times the cosine of the angle 1, so this angle from our positive x-axis to 1 would be theta 1. And then, so that would give us our x value of acceleration, and then we're going to add acceleration 2 from mass 2 multiplied by the cosine of angle 2, which once again is just going to be the angle from our positive x-axis to our acceleration vector. So from here to here would be acceleration 2. And then we're going to add our acceleration 3 multiplied by its angle, and once again it's just going to be this angle from 0 to wherever our acceleration vector is. And so this is for the x direction. We repeat the same thing for the y direction, only we're going to be using sine. And then of course we could solve for a3 cosine of our third component from mass 3. We're going to solve for that, just moving our first two terms over, and we can do that for x and y. So from here I'm only going to solve for the one direction as we go, but as you'll see, actually I don't think that's true. Let's just take a look. So anyways, looking at these two equations, we don't know we could solve this a couple different ways, but I decided to go ahead and divide these two equations by each other in order to get rid of our magnitude of our acceleration 3. Because right now we don't know our angle 3 and we don't know our magnitude of acceleration. So if we divide these two equations, this equation by this equation, we end up with this term. Our negatives will cancel and our acceleration will cancel on the left side, which we could simplify this If we just take the inverse of each side of these, just flip them over, we'll have sine over cosine, and which is just tangent, and then on the right side we're just swapping the numerator and denominator. Okay, so at this point it should be clear. Just to find angle 3, all we need to do is take the inverse tangent, which all I did was move or take the inverse tangent of both sides, and then we need to plug everything in. So we represented our acceleration as just a1 and sine of theta 1, but we're not told both of these. But what we do know is that our acceleration from this relationship here is just going to be big G m over r2. So our mass divided by our radius squared. So we'll substitute that. We have our mass 1 divided by, this is our radius 1 squared, x1 squared plus y1 squared, and then normally we'd have the square root, but since we had to square it because of this square here, we don't get that. And you'll notice the big G is missing in all of these, and that's because each of these terms all had a big G associated with it up here. I guess I should have shown it, but basically the left and right side of the equation all were dependent on G, so we got rid of that. And then so here the second term is coming from sine of theta. We know that the sine of an angle is equal to the opposite, so in this case our y value we're replacing divided by our hypotenuse, and in this case that's our radius, which once again is just our using Pythagorean's theorem, we got x1 squared plus y1 squared and the square root. And so we go through and do the same thing for each of these terms, represent them in what we know. We know our x and y coordinates, and we know our mass. So I did the same thing here. And then in the denominator, it's all the same except what our value is when we solve for our trig function. So in the denominator, we have cosine instead of sine. So it will be our x value instead of our y value. Other than that, everything else is going to stay the same. So when I plugged all this in, I ended up with the calculator spit out an angle of 75 degrees, I believe it was. Yeah. And but that doesn't make any sense, because if we look at this, it's giving us an angle somewhere in this direction, right? But we know that if we put a mass over here, that everything's going to be pulling upwards, and we're going to have some sort of an acceleration. So what we're really getting, what we really want is the opposite. So all we need to do is add 180 degrees to that angle that you'll get when you plug it in your calculator, which ends up being this 255 degrees. It's just 180 plus our 75. And so I didn't write it out here, but in order to find our distance, where our location of our mass 3 is, how far it is from the origin, we could just go back up and solve either of these equations here. We had our two equations solved for one for the x working in the x direction and one in the y. I chose this y equation for some reason, I don't know why, but I plugged in my 250 degrees, and we have to do the same thing where we substitute our acceleration and our sine of angle 1 and sine of angle 2. I suppose you could have solved for all that from the get-go and plugged it in. But I just kind of derived it and plugged it all in. And after dividing this term by our sine of our angle that we just found, we find that our magnitude, our radius is going to be, R3 is 1.78 meters from the origin. So as I've said in the past, I don't care if you guys want to leave an answer in polar coordinates like this, where we have an angle and a radius, or if you felt more comfortable because we're given Cartesian coordinates to convert that back. But I personally wouldn't waste my time. And it just dawned on me that I said I plugged in our angle here and solved, but that would give us the acceleration. So really, after you plug that in, what we need to do is solve by plugging in this equation as well, for A. Anyways, if that's confusing, just let me know and I will explain that further. Okay, so now that we know how to find the force and balance our force or accelerations, let's take a look at how we would determine if we wanted, if this was some planet with a mass of 2.4 times 10 to the 18 kilograms, and we want to project something off this planet, shoot it off the planet, and have it not return, what velocity would we need to shoot that object off? And we're told that our planet has a radius of 2,700 kilometers, which will be important as we figure this problem out. So the important thing is, if we think about this in terms of energy, is we know that work equals a force over a distance. And we also know that work equals the change in kinetic energy as long as we don't have loss to something else, friction or some other outside force. We're going to ignore that and assume that all the work that was put into this object is going into its kinetic energy. And so what we could say is that our change in kinetic energy equals the integral, because our force isn't constant. We can't just sum it up or multiply by some force. We need to take the integral from our initial position to where we want to get to, which we're starting on the radius of, I put an E here, but I guess it should have been P, the radius of a planet, this planet we're talking about, and we're going off to infinity because we don't want to return. And then we know we're integrating over that force. Well, we know our force is from Newton's law of gravitation is equal to big G, mass of the planet, mass of the object that we're shooting off, divided by the radius squared. And so we're going to be taking the integral over this radius. And so the left side of the equation, our final kinetic energy when we get off to infinity is going to be equal to 0, because we just want the minimum velocity to get to infinity, if that makes sense. It's more of an idea than anything. And then we're going to subtract that from our initial kinetic energy, 1/2 the mass of our object that we're shooting, multiplied by the initial velocity, which is what we're looking for, our escape velocity that will be. And then that's equal to our taking the integral. Well, looking at this, it's r squared, which we could think of as r to the -2. When we integrate, we want to increase that value by 1, so it would become r to the -1. We divide by that, so that's where this negative sign's coming from here. And then we'll have r to the -1, which is just the same as saying r to the 1 in the denominator. And then we need to apply our boundary conditions, or our limits of integration, rather. So we're starting at the radius of the planet because we're on the surface of it, and we're going off into infinity. So when we plug that in, our first term, well, divide whatever's in the numerator divided by infinity gives us this 0. And then our second term is going to be plus our GP, or our gravitational constant, multiplied by the mass of the planet, mass of the object, divided by the radius of the planet. So all we did was plug our radius of the planet in. And so we could simplify this. We see that both sides are dependent, have the term of the mass of the object, which is good that they cancel out since we weren't given a mass of the object. And our, what else? I guess that's it. So solving for this, we get a velocity of our initial velocity that we need. Our escape velocity is equal to the square root of 2g, the mass of the planet, divided by the radius of the planet. And of course, these are all known values that we were given in the beginning of the problem. And we see that we have an initial escape velocity from this planet of 10.9 meters per second. So that answer is pretty small. it seems like a low velocity to be escaping from a planet, but that's because our mass of the planet is pretty small, 2.4 times 10 to the 18 kilograms. Earth is a factor of 4 times or 6 times that, I believe. Let me double check. So I just looked it up. The escape velocity for Earth in these idealized conditions is 11,200 meters per second. So it's significantly larger. But as I said, the mass of the planet Earth is 5.972 times 10 to the 24. So it's a factor of 6 greater. But plus the radius of the Earth is a little larger, so that will also affect it. Okay, and so in our last example today, we've worked problems like this where, ignore all the blue lines for now, just this mass 1 has some distance r, it's separated from mass 2, and we've looked at that and we've solved the problem where basically mass 1 was much, much greater than mass 2, and if you follow this black circle I got, is supposed to be the orbit it would have taken if mass 1 wasn't moving, if it was much, much larger than mass 2. But as you can see in our values given in this problem, mass 1 and mass 2 aren't that different. The mass 1 is order of 2 times the magnitude of mass 2. And this is important because what happens when we start having masses that are similar in size is where they rotate is going to change. So what I have here is I've drawn this dot here, and it's supposed to represent the center of mass. And this is, if you remember from our rotational motion, objects rotate around their center of mass. So if we think of this as one system, instead of mass 2 orbiting around mass 1, we could just keep this as a fixed position. We now need to consider how they're both rotating from the center of mass. And so I have drawn the radius 1 much smaller than the radius 2 because, just as an assumption, since mass 1 is bigger than mass 2, our center of mass is going to be closer to it. And so if we don't remember how we calculate the center of mass, we just need to take the mass times the radius of the object from whatever point we're considering, plus the mass, the other mass times its radius. So the easiest thing to do here is, because we know how far it is from the center of one of these objects to the other, we're told that, is to represent radius 1 in this for here as 0, and radius 2, make this our origin, and then radius 2, we know we could just pretend it's along the x-axis and is out at radius, our radius that's given. So when we plug all that in, we end up with a radius center of mass of 3,499. So all I did here, I guess I had forgotten to write it. All we did was plug in mass 1 for mass 1. Radius 1, like I said, I called 0. So really this term disappears. And then we added mass 2, which we're given 2.1 times 10 to the 5 kilograms, multiplied by radius 2, 7.2 times 10 to the 5 meters. And then we just divided by the sum of the masses, just added mass 1 plus mass 2. And we end up with a radius center of mass of 3,499. And so what that means is, how we define our coordinate system is that this is how far it is from the origin, 0, which is where we located mass. We defined it being located at mass 1. So what that tells us is that our radius 1 is equal to our radius of how far mass 1 rotates around this center of mass up here is going to be equal to this distance we came up with, because we went from the center of mass to not our center of mass. We went from the center of mass 1 to our center of mass, which is this calculation, how we had it defined. We could have defined it any way we wanted, but to me that was the easiest. And then our leftover distance, all we need to do is subtract our total radius by the radius of center of mass, our R1 value, which should make sense because R1 plus R2 should equal our total distance of separation. And so what that comes out to be, as I said, is our R1 equals our radius center of mass, and R2 is going to be 716,501 meters. And so at first it might seem like we did something wrong because R1's so much smaller than R2. But also, if we look at our masses, our mass 1's much larger than mass 2 by a factor of 2. And so if we look at how our factor of the difference in magnitude of these two, if we moved our decimal place over and added 1, 2 more, we would have approximately the same magnitude. It would almost be split 50-50. And so now that we have our radius R1 and R2, we should be able to answer any question we really want to answer about this. We should be able to come up with orbits if we could find the velocity of each of these, which we'll be able to do. And so the important thing when we have the situation where we are where we don't have some mass that's anchored in the center and we're rotating around that is knowing when to use which distance, R1, R2, or just our total distance R. So when we're thinking about the force of gravity, it's just going to be our big R, right? Because it's the total separation distance of those two masses between mass 1 and mass 2. But when we think of our centripetal force, we have the mass of whichever planet or object we're interested in multiplied by the velocity of that object and then divided by the radius, that's its radius from the center of mass. So when we're talking about our centripetal force equation, we need to consider the radius from what it's rotating around, which would be the center of mass. So here we would use the radius that goes with whichever mass we're talking about, and here we would use the total distance of separation. So I'm not going to really work any more problems with this. We've seen most of this before. I just wanted to clear up and make sure you guys know when to use which radius. Hopefully it's starting to be clear when we're talking about gravity. It's going to be the distance separating those two. When we're talking about centripetal force, when we're talking about rotating something around, it needs to be the radius of the circle it's traveling. And so if we look back up here, like I said, the black circle would have been if our mass 1 was much, much greater than mass 2, but in this case it's not. So now we see that our orbit shifts. Mass 2 is going to shift a little bit and not come quite out so far over here because now its center of mass is a little closer to where it starts here. So hopefully this was helpful. There isn't a whole lot of homework I added for gravitation just because it's a lot of stuff that we've already seen, but I just wanted to make sure that you guys weren't confused about any of those concepts. So let me know if you got any questions, and I'll be making another video soon. Take care.